gonna start recording this lesson. So yeah, first let's talk about the homework from yesterday. So milk scheduling. Um, and yeah, here's my solution. So we need to parse the inputs first, right? So for each cow, there's the milk time it takes to milk. Uh, and then for each cow, there's also a list of dependent cows as well. So we want to store that. Um, also, I have like a dependency count array, so that for each cow, when we do that simulation, when the uh, number of dependent cows reaches 0, we go ahead and put that in the priority queue. Okay. So we have a priority queue of cows. Well, we sort them based on the milk time, and we initialize the priority queue by putting cows that don't have dependencies um,
I'm not I'm not able
into the
to see
priority
your
queue.
camera at all.
No, I think I turned it on. Are you able to see my screen share,
Yeah,
but not my camera?
yeah.
Um, hmm, that's weird.
Now I can see it.
Okay, all right, there we go. All right. So yeah, with the priority queue, I'm prioritizing the cows based on uh, the end time uh, that the cow will finish. Okay, so I use this process where I loop through the priority queue, and every time I remove a cow, uh, and afterwards uh, I mark the dependency for those cows down. Um, for those cows that depend on it down by 1. Um, and um, if their number of dependencies reaches 0, I add it to the queue. Yep, so that's my solution. Questions on this? Okay. So what I want to do today is go over type of problems I like to call 2D simulation. Uh, and with this type of problem, it algorithmically it's actually not that difficult, but it is easy to make mistakes. Basically, like you imagine like you're in a 2D grid, like a 2D map, and you have to kind of traverse around that map by going up, down, left, right, or north, south, east, west. Um, so the first problem that we'll be looking at is called mirrors, and let me go ahead and pull that up. Not this one. There's actually 2 mirror problems. Yeah, this is the right one. Okay. So yeah, here's the link. So why don't everyone look at this for a few minutes. Okay, are we good? Yeah, so we have a 2D grid of mirrors arranged either like a slash or a backslash, right? It's like diagonal one way or the other way. And the problem is saying like if we shined a light um, from the perimeter uh, of this field inwards, like what's like the maximum bounces that uh, that beam of light can have. So if you look at the dimensions, right? The grid is m by m. That's a thousand. That's a million. Okay, so um, um, so that's a million cells in this grid, which isn't too bad. So we do need to simulate Bessie shining a light into it, right? And should be doing it from the perimeter. So the perimeter. So if it's a 1,000 by 1,000 field, then the perimeter there would be there are four sides, right? Of perimeters. So that would be a total of 4,000 possible starting locations for the beam. So let's see. Um, so 4,000, uh, and then there could be a million fields. Now, fortunately, we're probably not going to be bouncing through most of these fields. Okay, so we're going to do that simulation. We're going to try to do simulations where we just kind of shine the light in and let it bounce until it goes out of the screen. Um, yep. Okay, so how do we do this? Well, I guess first thing we need to do is set up the input for set up parsing the input. So why don't we do that first? I'm gonna be actually doing it in code. So let me generate the starting code. Um, hold on, where's my Eclipse? Hold on one sec. It's not the right workspace. All right, I gotta reopen Eclipse. Sorry. All right, so let me do the starter code first. So it's called mirrors. All right, so here it is, and now the map, right? It's either a slash or a backslash. So we can technically use like a Boolean 2D array to store that, but we don't really need to be that efficient. Uh, we can get away with using a 2D character array. That's totally fine as well. So I'm gonna call this map, and that's like literally the map of the field. Okay. I do also need to parse n and m, so let me go and do that. Right. Or actually, so let me just define one dimension instead of two, because when I parse the n rows, um, what I can actually do is call in.next, which returns me a string, remember? And to get the corresponding character array of the characters inside the string, you can do dot to char array. Right, so I'm using a jagged array here, which is fine. Okay, so that's the easy part. The hard part is we got to simulate us shining a beam in and have it be bouncing around. Okay, so let's think about the state of my light beam. Okay, so state of light beam. Right, we can think of it as we start a light beam at a certain state, right, and then when it's bouncing off a mirror, we're changing the state of the beam. Okay, so um, how? So what do we need to know about a beam to be able to figure out where it's going to end up and um, where it's going to bounce off of? So we need to know the positions, the row and col row and column number of where the beam is. Um, but that's not enough, right? We also need to know the direction of the beam. Okay. So the state of the beam can be written can be represented by three numbers: the current row and column position, as well as the current direction. Okay. Uh, with the direction, how do we represent that? Here's something I suggest people do when we're doing this kind of problem. We create constants to represent the four different directions. So north, east, south, west, right? So I'm going to say north is 0, east is 1, south is 2, west is 3. And of course, you can have different numbering conventions, but there's a very good reason why we want to choose the numbers 0, 1, 2, 3. And and in that order, in this case, a clockwise order, right? Um, so very specific reason why I want to use these numbers is I can represent the transformation of the state of a light beam before a bounce to after a bounce um, fairly easily. Um, so when a light beam hits a mirror, it changes the direction of the beam, right? And that directional change is dependent on whether it's like a slash or backslash, or like which diagonal it is. And that's like four different cases here, right? The four different directions they actually bounce uh, uh, very differently, right? So I want a way to represent given a light beam traveling at uh, direction dir, what is its new direction when it hits a slash mirror? And ditto for the backslash mirror. Okay. Now I can make four if statements, and I think that suffices. It is a bit clunky though. Here's a neat way to represent that. We use an array of length 4 where I'm calling it slash. So slash of I denotes the new direction after a light beam of direction I hits a slash mirror. All right. Uh, let me take a moment to actually draw out the geometry of it. It's not hard to figure out, but it's easy to make a mistake. So a slash mirror like this. So if my beam is bouncing off it by traveling north, then it's going to go east, right? So the way I would represent it in this array is at index 0, which is index north, right? It gets transformed to the east direction, right? And then the east direction, right? So if my light beam hits it in the east direction, it's going to bounce off southward, right? So the east direction gets transformed to south, right? So I'm going to put an S here. Okay. Uh, and if I'm traveling southward onto the mirror, then it gets transformed to westward, right? So I put W here. And if I'm traveling westward onto the slash mirror, it's going to bounce northward, right? So like that. Okay. So technically I'm using integers to represent the four directions, but yeah, don't actually use the actual numeric value. Don't actually use like 0, 1, 2, 3 in your code, because you will most likely get confused. Use these constants to help you try to figure this out. Okay. And why don't we do the same thing for the backslash mirror? So I'm gonna just call it b slash backslash. All right, and I'm going to draw again the same thing in Paint. If you're looking at my screen share, and again, it's not hard to figure out. It's just easy to make mistakes on it. So right, I want to figure out like what directions they get transformed to if we travel north, east, south, west onto the mirror. Okay, so if I travel north onto the mirror, it's going to bounce westward. So W here. Okay. And if I'm traveling east onto the mirror, we bounce southward. If I'm traveling south onto the mirror, I'll be bouncing off eastward. And the last one, if I'm traveling westward onto the mirror, then I'm bouncing northward, right? Okay, so there's that. Question on these two arrays. So it's a small little thing, but I think this helps us a lot in figuring out uh, the state of my light beam as we transform the state from one state before bounce to after a bounce. All right. Um, okay. So next here's what I want to do. There's something additional with the transformation, right? Uh, when we have a light beam of a certain state, and then when it bounces, it goes to a different state, right? It changes direction. It also changes position as well, right? And if a beam is traveling northward, then it's changing the rho value, right? If it's traveling north or south, is changing the rho value. If it's traveling east or west, is changing the column value. And we can actually employ the same trick here. Right, the transformation is going to change the direction. It's going to change both the direction and the position of the light beam. And using this same trick, we can avoid writing like 4 different if statements to change the light beam's position to new rho and col values. I'm going to call this array dr. Okay, so dr stands for difference or change. Difference. Sometimes in math it's also called delta. Delta in rho value. Again, it's 4 numbers. So these 4 numbers represent like if my light beam is traveling in those directions, like how does that affect the rho value? So if I'm traveling northward, then I'm decreasing the rho index by 1 technically, right? If I'm traveling eastward, then it has no effect on the row. If I'm traveling southward, that increases the row count by 1. If you're traveling westward, that's 0. Okay. I'm going to do something very similar to the column value as well. Call it DC delta, or difference in column value. And it looks like that. Okay. So armed with that, what I want to do is I want to loop through each position just outside of the field's perimeter and simulate shining light into it. Simulate a light shining a light beam into it. Okay. So let me start with the left and right edges. Okay. So I have to loop through each row and simulate going on the left end and shining a beam eastward, and then going on the right end and shining a beam westward, right? So let's loop through each row. And now, usually with a for loop, we use like I as our counting variable. We all do that. We all been trained to do that. I actually recommend for this kind of problem, don't use I or J. Use R for row, right? So I'm looping through rows here, and I want to start my row at R, and I want to start my column at -1. Right, negative column of -1 means it's like right to the left of the um, thing, right, of the field. And then the direction, in this case, I won't be shining it eastward, right? Okay. And so here's like the starting state of my light beam. And I don't have a function here yet, but why don't I make a function that, given the state of the light beam, it's going to count how many bounces it's going to have into the field before it comes out. Okay. So I'm going to write this function, uh, call it static int count bounces. It's going to take in the map, and it's going to take in the row and column value of the light beam, as well as the direction. Okay. So this function is going to count the number of bounces given the position and direction of the light beam. So it's going to simulate the light beam traveling by first change the position given the direction. Okay, then right. So it's going to start like just for example, like in the initial start state, right? It's going to start like just outside, right to the left of the field. And the first thing we're going to do is we're going to make it travel in the direction it's facing. In this case, it's traveling eastward, right? So it's going to travel and change the position given the direction, and then change the direction given the slant of the mirror, right? Yeah, yeah, yeah. right? And then that gives you another state, right? And then we can um, do the same thing to get us to the next state, and the next state, and the next state, and so forth, until the light beam is out of the bounds of the field. Okay. Um, yeah. So yeah, I'm gonna try to write this function here. So the new R value, the new rho value is going to be R plus um, uh, what is it? dr of dir, right? And the new column value is going to be c plus dc of dir, right? So we get the benefit of not having to write for if statements, right? To find out what the new value of the row and column is, right? We just look up what is the change in row and change in column given the current direction that we're traveling in. Okay, and then we look up this position and see if it's in bounds. That's important, right? So I am going to get the dimensions here again. Uh,
So I have a
yeah, go ahead.
question.
Yeah, go ahead.
What happens if it like bounces forever, like the problem says it can?
Uh, yeah, good question. We'll talk more about that. So when would we know that it bounces forever?
When it hits the right time limit.
When it hits around, right, there's only so many mirrors, right? And each mirror has two surfaces, and right. So if um, you can technically, I'm not sure if it's possible, but it's conceivable that you hit the same mirror uh, in all four directions, right? So there's at most a million mirrors, and if you've made 4 million bounces and you haven't exit out, then you then you're stuck in a loop, right? Right. So we want to check for whether the new row and column is in bounds. If it is in bounds, then okay, then let's also figure out the new direction. So the new direction is going to be dependent on what slant the mirror is, right? So if map of new R, new C is equal to forward slash, then my new direction is equal to um, what is it? Slash of dir, right? Else, then it's the other way. So we're gonna bounce off the backslash, right? So it's b slash here instead. Yeah. Great. Okay. And then what I can do here is now that I have a new state, right? So I've made a bounce. So here's an neat trick, recursion, right? So the thing that we did here, we just discovered our new states, right? Our new row, new column, and new direction. And we can use the same function to simulate the rest of the way, right? You don't have to do it this way, but yeah, that's it. Okay, so now that we have this, let's go and go back to the main and fill out the rest of the details. So we do need to simulate the bouncing of on all edges, right? And we also need to store the answer. Okay, so I'm going to say answer equals math.max of count bounces. You give it the map, you give it the start row, give it a start column, and you give it direction. Okay. All right. And you would also want to do the same thing on the right side, right? On the right edge. So actually the call here would be M, and the direction here would be west, right? Do the same thing here. All right, and then we rinse and repeat for the top and bottom edges. So in that case, this time we were counting through the different columns, right? So be careful here. Let's change the indices. Yeah, so this is why it's a good idea to use RNC to count, because you know exactly like which row and which column you're talking about. So the start row here is when -1. The starting column is going to be just C. The direction, we're facing southward, so we're doing the top edge, right? The row is -1. The direction is southward. Okay. And then here, I do want to change the column. No, I want to change the row so that it's the last row, and I'm facing northward. So I'm going in from the bottom edge. So yeah, that's my solution. I haven't talked. So like Vankit said, there is a possibility that we go in like an infinite loop. I have not taken account for that. So I'll talk a little bit more about that. You actually don't end up needing to do that with the test cases that they provide. So I actually haven't uh, add that into my solution, but we'll look at that together. Oh, I made a mistake here. Should have answer here, answer here, answer here, answer here. All right. But yeah, question on this solution.
So this is basically using recursion to see if there's a how many times it'll bounce in each row and column.
Yeah, because like this function here, it takes in the current state of the light beam, and it gives you and it calculates the new states, right? The new row, new column, and new direction, right?
Right.
And it's doing that to calculate the number of bounces, right? And well, in that sense, right, we can just use the same thing over and over again.
Okay. Yeah.
Yep. Okay. So one thing we can do here to terminate is we can add an additional if, right? So if the current count has exceeded a certain amount, then we can quit. So with my recursion, it actually is harder to do that. There's a way to do that if you parameterize an additional parameter to say like how many bounces we have so far. You can do it that way. On the other hand, if you want to do it using a loop, that also works as well. So what we would do here is here's the new R and new C value, and then so instead of saying if here, we're going to say while this is true, right? And then here we do we do the new direction, right? And then we increase the count, right? So we're gonna, so we don't do it recursively. We're gonna have to create a count variable. Okay. So we figure a new direction, right? And then, so we do need to simulate it moving, all right, changing position, right, and then doing the bouncing. But then afterwards, we do also need to do this again. So it goes to the new position, uh, and then the while loop's going to check whether it's out of bounds or not. Yeah, and then to prevent it from looping too many times, you can add an additional thing. And counts is less than n times m times 4, right? Right, because if it's exceeding that, then we're stuck forever, right? Okay, questions on this? All right, so I'm going to clear this, and let's look at another problem together. So this one's called build gates. So here's the link. Let's take a look at it. All right, how are we doing? Okay, so yeah, well, let's talk about this. So this problem is interesting. For geometrical problem like this, it helps to really draw out the sample input. Okay, so uh, the sample. So we're supposed to start at the origin, right? At position 0, 0, and then there's like a series of instruction northeast, southwest, uh, and it's basically asking us to count like how many regions we have segmented the field into. Um, right, so I'm gonna draw out. I'm just gonna try to simulate what uh, the sample input looks like. So let's say this is the origin. Okay, so you can look at my screen share for now. Right, so we go north 1 unit, oops, we go north 1 unit. So we build a fence here. So this is 1 unit, okay? And then we go north again, right? And then we go north again, okay? And then we go east. Oops. Okay, and then we go east. And then we go south. And then we go west. And when we go west, so notice that we've enclosed one region off, right? By going west like that, okay? And then west again. Ah. And then west again. Okay. And then south. Right. South. And then south. And then east. 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 So there's a total of 2 regions, right? So two rectangles here. Right, so how would we ever figure this out? One thing that we have to be careful, it says like Farmer John can backtrack sometimes. Right, it says here, his fence may even cross over itself if its path cuts through one of its fence that is already built. And Farmer John may visit multiple points multiple times, and he may even lay the same segment of fence multiple times. So how would we know when Farmer John has actually enclosed one region?
If or do it with you.
Go ahead.
Yeah. Okay. So if like say you have several like directions that are pretty much equal to each other. So you have north, 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 east, 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 south, 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 west, west, west. You basically have created you've basically gone in like a circle, or in this case a square, because you're using the same amount of directions with the same amount of times to get through, which is what happened with the first square there.
So can we reduce that to essentially if you've come back to the same place that you have been before, then you've enclosed a region?
Yes.
Mm,
Wait,
what if
what if you go north and then you like come back to the same spot?
oh yeah,
That
so what if I
wouldn't
go
be
north and I go south immediately?
Oh, that's
Yeah.
even if like actually if you're to say like go north and south and you put a gate there, does that gate build through both times you've gone north and south, or
Uh,
is it just
you can
once?
essentially treat it as one fence. Yeah.
Unless you're not layering them together.
Uh, well, you're layering it together into one,
But like,
but
but then the
yeah, okay,
gate
yeah,
will,
yeah, right, yeah, yeah.
yeah,
I know what you mean. Right, yeah,
think
yeah.
of it
So
like one thing. Yeah.
okay, yeah. So this does take some time to figure out. So let's say like I have um. So when you successfully enclose uh, a region, what would it look like? So you would be going into a point. So let's say here is where I am now. So if you're not looking at the screen share, please do. Okay. Yeah. So like this is where I am now, and um, to enclose this region, I would need to go west like this, right? What I can do is I can look at first of all, am I going to a new point that already has a fence there? Because if I am, then I would have to be enclosing a region. Well, actually, not entirely true, right? Like Victoria said, like if we go north and then go south, right? Technically, we've already placed a fence there, but then when we backtrack, it's the same fence. Or how about this? If we adjust it slightly, if we go to a point where there's already a fence and we're not actually building a new fence going into it, right? So, right, if I'm going back to my original point, and as I'm doing that, if I see that at that point there's already a fence there, there's at least one fence there, and my traversing back to that point is actually building a new fence. So if both of these are true, then I'm actually enclosing a region, right? So yeah, let me write this down. So we are enclosing a region if one, we are going into a point that already has has at least one fence in any direction. Okay, and two, we are laying down a new piece of fence when going into that point. Let me put that in the pad as well. So if we're going into a point that already has at least one fence in any direction, and as we're going in, we're actually laying down a fence. So that particular path that hasn't existed before, then we would know that we've just enclosed the region.
When you're trying to count how many fences you need, like, are you going to say like if there's for every enclosed region we have, I'll add one fence to it? Because that wouldn't work if you have something like say if you have like two.
Wait, hold on. Let's be clear. We're trying to count how many regions we've fenced off, right? We're trying to find how many gates we need, right? And that's like how many regions we've enclosed, right?
Yeah.
Yep. So your question is,
Because
can you
if
repeat
we
what your
like
question is?
so if they like, try to count how many enclosed regions we have and give a fence, give a gate for that, are we trying to do that? Because if we do that, say you have something like two enclosed regions side by side, then what would happen?
Oh. Yeah,
You
then
can
we need four fence, technically.
yeah.
Right. So we're assuming that they don't need to be um, they don't need to directly connect to the world. Even like so, in a more extreme example of what you wrote is if we have like a we have like a 3 by 3 grid of fence, like that looks something like this, like um, right. Let's say like this is my fence orientation. We would still say 9 because like if we build a fence, uh, if we not if we're not actively trying to break this, it's possible to build just one fence per region, so that it, all of this can be reachable, right? Even the inner one, right? You would just have to go through 2 gates, right?
So
Does that make
basically,
sense?
you're trying to make it so that from any square that you're in, you can navigate to any other said square.
Right. So don't worry too much about the actual navigation thing, we are going to just be counting number of regions that we have, essentially.
Okay.
Yep.
Because if you were like say you have the entire region and you just split it in half, then you only need one gate for the two enclosed areas to connect one half to the other half.
Correct, but then you would need another gate to actually get out of that enclosing region as well. So really, you're just
What if
counting
it's
the
the
number.
entire region? If it's the entire field, if that's the region.
You have to go out to infinity. Okay.
Oh, it's infinite. Okay, all right.
Right. So here we need 9 fences. Okay.
Yeah.
So don't overthink it. We're just counting number of enclosed regions, and here in this example, it's 9. Okay.
Right.
Yep. Yep. Okay. So we have an idea here, right? So if we are going to the point that already has at least one fence in any direction, and we also laying down a new piece of fence by going to that point, then we are actually enclosing a region. And you can think of weird examples where which this still works. So for example, let's say your path looks something like this. So you go and enclose one region, and then you track this side again, and then you go like that, and then you go like that. Oops. And then you go like that, and then you go back like this. So that algorithm still works. So here we're going into a point that has at least one fence laid down already. And we are also building a new piece of fence as we're going into that point. So yeah, that actually satisfies our two conditions here, and we're indeed building a new region, right? So yeah, so looks like this should work. And then you can think of more examples, right? Where like maybe I do this, and this will still work. Okay. So now let's talk about representation of the field. Okay. Yeah, one thing that's really hard about this is, so we have our different positions, right? So we start at the origin, and then when we go north, right, we go to the point 0, 1, right? That's my new coordinate. But then when we store the fence, one thing that we have to grapple with is uh, it could be in like any of the 4 directions, right? Fence or belt in between points, right? So how would we represent that? There are a couple ways. So we can, for example, have a list of points. Okay. And by the way, yeah, we really can have a list of points here, right? Because there's 14 instructions, and we start at the origin, so there will be a total of actually 15 points, right? So we can have like an array of points where it looks something like this. So points of I0 and points of I1 denotes the x, y coordinates of point I. Right. And again, the +1 here, it comes from the fact that if there's like 3 instructions, right, then we go like north, north, north. There's actually a total of 4 points here. There is the origin, and then you go one step, one step, one step, right? So it's a total of 4 points if there are 3 instructions. So if there are n instructions, there's a total of n plus 1 points. Okay, so there's that. And for each point, we need to store the fact whether it's north, east, south, west directions have fences, right? Yeah. So there's a couple of ways of doing this. In the solution, the in the solution, in the user code solution, what they did is they figure out there's only 1,000 steps, right? There's only at most 1,000 instructions. So at most, the range of our coordinates are between -1,000 to +1,000, right? That's like the highest. So what we can do is we can create a Boolean 2D array, and this is going to look weird, of size 2,000 by 2,000. Actually, is that right? No, 4,000 by 4,000. Okay, so why 4,000 by 4,000? So there's actually 2,000 numbers between 2001 numbers between -1,000 to +1,000, right? And since we can't actually use negative coordinates, negative indices into the array, we are just going to shift it so that x coordinate of -1,000 will be transformed to and y coordinate of -1,000 will be transformed to map of 0, 0. Okay. So that doubles the size here, right, to 2,000 by 2,000. But then I did 4,000 by 4,000. Why is that? It's because if I scale the map by another factor of 2, what I can do is at each point, at each move, instead of moving 1 step, we move 2 steps. And so that means like we start in the origin and then we go north. We don't go to 0, 1, we go to 0, 2, okay? And then if we go north again, we don't go to 0, 3, we go to 0, 4. Why is that? It's because if we have that extra gap there, we can use it to store whether there is a fence there. Does that make sense? Right. So essentially, we're blowing up the map. We're scaling it by a factor of 2. So every step you're traveling 2 units instead of 1 unit, and that way we can use the odd coordinates to specify whether there is a fence there or not. So that's the way the user solution did it. The way I did it, I use a different representation where it maps a point to a Boolean array. Actually, don't ever use an int array as a key, because int array's hash code doesn't work properly. So you're going to have to define your point class if you want to do something like this. So basically, I want to map a point. So I have a class point. So this is an alternate way to represent the map as well. So this is an alternate representation. So this hash map here, it maps a point to a Boolean array of length 4 to denote whether there is a fence at the 4 directions of the point. All right. Yeah, either way it's going to work, and I'll let you guys pick which one. Just be careful if you define a point class, make sure that you define the hash code function. All right, so that is it for class. Any questions before we go?
How exactly does like the Boolean map work?
So it maps a point to a Boolean array. So the keys are points. Okay, so for each point, I want a value associated with it, and that value is whether there is a fence in the north, east, south, west positions of that point.
Right.
Does that answer your question?
I see. Yeah. So the Boolean is two things. How can it be north, east, south, and west is 4?
Well, it's a Boolean array.
Oh, okay. Yeah.
It's a Boolean array of length 4.
Right. So you can just map it out to depending on over which one you want to go to.
Yeah.
If we created the class point, would we have to write like an override function, or would it not be?
Right. So exactly, you would have to override the public int hash code function.
Okay.
And a sensible solution of what you want to put in order for the hash code to minimize collision would be something like this. You can even do like a million here to be absolutely sure. But yeah. Yep. So yeah, I'm gonna have this for homework, and I will see you all tomorrow.
Do we want to physically map it out, or do we just want to like represent it?
You want to do whatever you need to do to answer that question.
Okay.
I guess you do have to simulate all the steps, right, in order to figure out like at what point where you would be, right?
Right.
So yeah. All right, I'm gonna head up. See ya.